This video is going to give a brief discussion of elastic collisions. We're in the discussion now of conservation of momentum. Just a reminder, momentum is mass times velocity, kilograms multiplied by meters per second. And Newton's second law is here. The net external force equals the change in the momentum over a time interval where that change takes place. So this is average force. What happens if the force is zero? Well, to have force of zero, that means the change in momentum is zero. And the way that this relates to the momentum is the momentum's constant. The final momentum is the same as the initial momentum. So if we'd subtract these two, that's the delta operation, then we come up with zero. So momentum is conserved if the net external force is zero. Momentum is conserved in both types of collisions that we'll discuss. In this video, elastic collisions. In the elastic situation, the kinetic energy of the system is constant. We're not going to have any losses of energy. And the objects will not stick together. The objects are going to bounce off of each other. Truly elastic collisions happen at the atomic level or subatomic level. More common are the inelastic, and in this course we will consider completely inelastic, where the objects stick together, and the kinetic energy definitely is not constant in this situation. Momentum, however, is conserved for both types of collisions. Even though the energy is not constant, momentum is conserved. So elastic, the objects bounce off of each other, kinetic energy is constant. Inelastic, the kinetic energy is not constant and the objects stick together. Well, there's some algebra that goes with conservation of momentum and conservation of kinetic energy. When you do that algebra, then you get the following relationship here. And I did not subscript these, but there are no powers of 2. This is the velocity of object 1 after the collision equals velocity of object 1 before the collision times the mass of object 1 minus the mass of object 2 divided by mass of object 1 plus the mass of object 2. And a second term, 2 times the original velocity of object 2 multiplied by mass 2 and divided by the sum of the masses. The second object, its new velocity, so this is v sub 2, the new velocity after the collision, 2 times the original velocity of object 1, mass calculation, minus, notice there's a minus sign in this formula, it's plus for the second term for v1, but minus the original velocity of object 2 times the difference of the two masses divided by the sum of the two masses. So we'll do some problems in the course I teach with this, but I'd ask you a question. How does this simplify if m1 equals m2? If m1 equals m2, so we're a billiard ball type collision, the two masses are equal. Well, m1 minus m2, that's going to produce a 0. This whole term is 0. And m1 equals m2, so I'll have 2 times m here, and there's 2 times m here. If you're following along, the object 1 takes on the velocity of object 2. Take a look down here. Now this term is a 0. The m1 minus m2 creates a 0 factor. And again, we've got 2m down here. These masses are the same. I have 2 times m up in the numerator. And object 2 comes out with the velocity of object 1. So there are other situations you could do to simplify if one mass is really big or one mass is really small. And my students will see that in class. So we have the elastic collisions. We can easily calculate using the principles of conservation of energy and kinetic energy and momentum. The algebra gives us these two equations and gives us a easy way to do the calculation. Here's an example: small mass, large mass, and a frictionless surface. Why does the surface have to be frictionless? The net external force has to be 0. Friction would be an external force, so we need a frictionless surface. And in this situation, mass 1 comes in here, bounces off of mass 2, and heads back to the left with less velocity. Typically, it depends on the masses, of course. But we then have object 2 traveling off to the right. So keep reading, work some problems.